Alright guys, today we're learning about the HR diagram, star classification, and survey, which is also known as Lecture 13. We're going to have a lot of diagrams in this lesson, but we're really going to talk about how we classify stars and how the HR diagram helps us. We're going to start by creating a classification of students to help explain the whole idea of the HR diagram. What we can see here is that we have an x-axis and a y-axis. Our x-axis is paying attention, y is their grade. And it goes from F to A and 100 to 0, all right? What we see in the middle here is something called a normal expectation. Basically, what we expect is if you pay attention pretty much 100% of the time, you should essentially get an A. If you don't, you should essentially get an F. Well, there's these things called anomalies. Students that pay attention all the time but still manage to fail. These are going to be our difficulties in science, so we're going to call them difficulties. And then you have the group that they pretty much pay no attention but still get an A. This is our genius. These are our anomalies. And stars do this too. Stars also have anomalies. And this is essentially what we're going to see on the HR diagram, is that there's going to be a normal expectation, or basically what we would call main sequence stars. And then we have our giants and our dwarfs, which are our anomalies. The classification of stars have to do with their different properties. Their temperature and spectra, which becomes our x-axis, the luminosity and absolute magnitude, or the energy emitted, which is our y-axis, with the spectral class being on the top, which is our another x-axis, but the same as temperature with temperature at the bottom. So you essentially have this square. And our y-axis becomes absolute magnitude, with temperature here, spectra here and temperature down here. Sometimes they do have both on the bottom, but generally this is how we form the Hertzsprung-Russell diagram, or the HR diagram. You don't need to call it the Hertzsprung-Russell, it is from henceforth now going to be called HR. So in this diagram, there are also areas like our student classification diagram. Main sequence stars are your normal expectations. If they are cool, they aren't luminous, versus if they are hot, they are very luminous. Giants are the equivalent of our genius section, where they're very cool, but still very luminous because they're very large. Remember, luminosity can increase with an increase in a star's radius, or diameter. And dwarfs are our difficulties section because they are very, very hot, but they're not very luminous, and that is because they are actually quite small. These are named white dwarfs because these were first observed appeared to be glowing with a white heat, and the name has stuck even though we have now found some cooler than our sun. There are some things we do need to remember from our last lecture. First is luminosity class, meaning the same temperature or spectral class but different sizes. Basically, you can be the same exact temperature, but because you are different sizes, you have a different luminosity class. You will give all, you're more luminous or you're less luminous, and this is where we get things like bright supergiants, giants, main sequence stars, and dwarfs. We also have our absolute magnitude, which going from -5 to +10. 0 to 5 means that a star is 100 times brighter, or 5 to 0, 100 times brighter. The Hertzsprung-Russell diagram is named for the two astronomers who independently discovered its usefulness. And these are the Danish astronomer Ejnar Hertzsprung and the U.S. astronomer Henry Norris Russell, and they call it HR for short. They independently discovered its usefulness pretty much around the same time. They didn't talk to each other, they didn't work with the same people, completely separate, same idea. And they realized that the diagram represents patterns suggesting relationships between luminosity and temperature, which basically is an insight into the nature of stars. And here is what our HR diagram looks like. On the bottom, for this variation, there is the spectral classification O to M, and the temperature in Kelvin, showing increasing and decreasing. And on the left, we have luminosity in solar units. The sun is 1 solar unit, and our sun is right here. And so our sun is equal to 1 solar unit. Dwarfs are in the bottom left. You have main sequence in the middle, which is our normal students. We have giants up in the right, which is our genius section. And we have our white dwarfs at the bottom left, which is our difficulty with science section. Because again, look, they are O to A class stars. They are very, very hot, but they are not as luminous, whereas these stars up here, like Betelgeuse and Taurus, they are super duper luminous. They have a 10 to the 5 to 10 to the 6 luminosity in solar units, but they have a temperature of about 3000 Kelvin. Again, it is because they are so big. Going with this, we have another correlation. Lifetime and size. The larger the radius of the star, the more luminous it is. And there is also a correlation that the hotter the star is, the shorter its lifetime, as it will use up its fuel faster. Within the giants, there are also variations. You have the red giant, the blue giant, and the yellow giant. And this all has to do with their temperature, how hot they actually are. Over here, we see our one solar radius, which has our sun falling on it. And so it is equal to that nice one. Lifetime also correlates, like I said before, with temperature. Our sun will have a lifetime of about 10 to the 10th years, whereas if we go higher, so let's look at Centauri Beta, their lifetime is only about 10 to the 7th years. We also found a correlation between the mass of a star and its luminosity within main sequence star. The greater the mass, the greater the luminosity. This trend of masses among main sequence stars is actually known as the mass-luminosity relation. For main sequence stars, this is L, or luminosity, equals mass to the 3.5, meaning luminosity can vary from m to the third and m to the fourth. M and L are given in solar units. An example is a star that is 10 times that of the sun. We would say, okay, luminosity, our M in this case, is 10. So 10 to the 3.5 is equal to 3 times 10 to the third, so about 3000. That's the luminosity. We're also able to see the luminosity classes within the HR diagram, which is super interesting. So remember, we have all these different classes, their description, and examples. What we have here is our white dwarfs. They are going to be our 5 or main sequence stars, which is also right here. When we go up, we're going to get to subgiants, which is right about here. And then we have giants, bright giants, supergiants, and bright supergiants. And this all has to do with, okay, how hot are they versus how luminous are they? Meaning, how big are they? I want you to pay attention here with our main sequence. We have some main sequence stars that are super duper hot and therefore very luminous, just as luminous as our bright supergiants, which are much cooler, only about around 10,000 Kelvin. So let's compare it. Let's put this in a little bit of a perspective for us. This is a version of the HR diagram that compares the known world to the stars. We can see that us, as the astronomer, we're in the bottom right corner. Being a lower temperature and size, we are not as luminous versus the, let's say, a blue whale, which is much more massive than us, and so has a greater luminosity. A medium-sized lava lake has a much higher temperature, not that much bigger than a blue whale, but it has a higher temperature, and so therefore a higher luminosity, versus, let's say, Jupiter, Earth, Mars, Moon, Venus are our own planetary bodies, where they're not much hotter than us, but they are way more luminous. And then we have our main sequence up here, brown dwarfs, white dwarfs, and then this is essentially our HR diagram that we see every time we look at one. Fun stuff. I like how nuclear fireballs are on here too. They're about as luminous as France. What can we actually use the HR diagram for? We can determine a star's nature. We can determine a star's luminosity class. We can determine a star's classification. Is it main sequence? Is it giant? Or is it dwarf? Tracking a star's changes, such as going from a baby to main sequence, to giant, to death, and tracking star formation. And this is where the HR diagram gets really interesting. To track a star's evolution, you can plot its path on the HR diagram. Its position on the diagram changes when its surface temperature or luminosity changes, and this occurs when there has been a change in its interior, and this is very important. The interior of the star is what makes it a star. A great way to think about this is to compare the populations of people height strength diagram. What we have here is we have on the X height in meters and strength in kilograms. Let's use a large example of people to measure height and weight that they can lift. 1 point is equal to a person. So if we tracked everything from infant to old age, we can see that essentially there's a trend as the older something gets, it can increase the amount of weight it can carry until it reaches old age, and once it hits its peak, it only goes down from there. But there are those who are shorter that can lift more weight. For example, we have people up here who are shorter but can lift a lot of weight compared to someone who's tallest and can't lift as much weight. Like we have those who, again, we say they're in old age, but they're very tall, but they don't really carry that much weight. This is where we're getting our giants and dwarf regions. And what you want to think about this here is, well, we can trace an individual through their lifetime, and we can find that as they got older and so taller, they would be able to lift more weight, losing strength in their old age, which is our red line. And we can see where to look at the blue line, where we see an individual moving above the main sequence as they aged, which is our line over here. We can see that they kind of move up here. They become into the giant area before going down. What does this mean? Well, they were stronger than the others. Maybe they did more weight-related work. Maybe they were a weight trainer, or they professionally body lifted, or their job just required them to lift a lot of material or heavy machinery. So why would they have lost all this strength? Why would they suddenly not be able to carry as much weight anymore? Well, maybe they would be more likely to suffer from a debilitating injury and so fall below the main sequence. Every person's track in this will be similar, creating certain patterns in the diagram, such as our main sequence, what we expect, our giants, and our dwarfs. And this can actually get kind of complicated, as can be seen in the paths for stars in the HR diagram, where they kind of go all over the place. But basically what you're seeing here is birth, main sequence, and then they go to the giant phase and then death, which, depending on how they end their life or how massive they are, they will become a white dwarf, or they'll die as a supernova and become a neutron star or a black hole. Generally, you have birth, main sequence, giant, death, and those are the stages of the life cycle in the most general terms. Pre-main sequence stage stars are plotted on the HR diagram. They are actually above the HR diagram themselves, as they are still shrinking, and therefore they are larger and brighter before they become main sequence stars. So basically, I am a baby star. At this point, I am quite big. I am known as a protostar. I'm quite big, so I'm giving off more luminosity just because my diameter is greater. And as I form into a star, I actually will shrink, meaning my luminosity will drop until I hit main sequence, and main sequence is where I am now stable. This is where I'm going to spend the majority of my life. This is when, guess what? I am an adult. We go baby all the way to main sequence or adult stage, where you are now doing what you want to do. You're in your 20s, let's say. You're now a fully functioning adult. You have stopped growing. Done. With protostars, there are T-Tauri stars and Bok globules as well. And the T-Tauri stars are variable stars. They have erratic brightness. And Bok globules are dense, dark blobs within contracting interstellar clouds. This is a representation of a group of young stars here in this figure that do have both of these. T-Tauri stars are also surrounded by gas and dust from star creation. And with more massive pre-main sequence stars, they will actually reach main sequence faster than less massive stars, which is interesting. So it is the protostar or baby star's mass that is the most important variable in determining how long this stage in star formation lasts. So basically, if you have more massive protostars mixed in, everything will become main sequence faster. Everything matures faster because those bigger stars are sucking up more energy than everything else. And so you can actually have a very interesting result from this, is that you will have the formation of brown dwarfs, which are stars that never actually make it to starhood because they don't have enough material to actually become massive enough to make a star. And that's because there were all of these much larger, more luminous stars that are basically naturally formed giants that are sucking up all the material that they need instead. As protostars finish accretion, or basically finish sucking up stuff in order to make themselves the correct mass, they will drop in luminosity to a constant temperature. As protostars begin their main sequence phase, which are illustrated by our dotted red lines here, lower mass protostars like our Sun will finish accretion or shrinking, and then drop in luminosity at a constant temperature, which is our solid red line. Here's where our zero-age main sequence is, and this is important, and I'll tell you why in a second. But basically, once they get here, we're going to drop to a very specific temperature, and there's basically our sun. Well, our sun's actually right here. Stars will settle into a configuration where it is hot enough in its core to conduct hydrogen fusion stably, and this is when we get that zero-age main sequence line. This is when the star finally settles into stable hydrogen fusion. For a star like our sun, pre-main sequence stage will take about 20 million years, but for a high-mass star, it's going to be about 1/10 of that, and for a low-mass star, it may be as much as 10 times longer. The difference in duration of protostar stage explains why the higher mass stars have already reached the main sequence, while lower mass stars are still in the protostar stage. These varying timescales for formation imply that the more massive stars may also influence the formation of lower mass stars. As in, due to their heating and ionization of a region, the radiation and stellar winds formed may limit the growth and lower mass stars. So not only are they sucking up all this material for themselves, the fact that they are getting closer to main sequence faster means that they start conducting hydrogen fusion, which is how they start to make energy. And this process pushes out these stellar winds, and the stellar winds, which is all radiation-based, is going to push the rest of the material away from this baby star nursery, essentially ending the star formation sequence. Stars change relatively little as they live during their main sequence phase, but they do change some. Stellar structure models tell us that a star depletes the hydrogen in its core, meaning that hydrogen nuclei becomes more spread out and less likely to collide, and the decline in energy production causes the star's core to contract slightly, compressing and heating the core greater, driving up the temperature until the overall rate of the reaction once again generates enough heat to support the star. During this time, the main sequence phase of a star will increase in luminosity by a factor of 3, causing its atmosphere to expand in response. During this change in luminosity, it's pretty impactful on the HR diagram, which has a factor of over 1 million luminosity. The change leaves the stars in a narrow band, beginning with the zero-age space and ending space. Okay, so we have our zero-age space and ending space. Zero-age, end of main phase. So they kind of will rise up in this until they get to their end phase. And once they hit the end of the main sequence, hydrogen fusion will start to end. It is possible to estimate how much a star has aged based on its shift from its expected initial characteristics at the zero-age main sequence to where it is on the HR diagram. This requires precise measurements of a star's mass, luminosity, temperature, and chemical composition. Although changes are relatively small compared to how much the HR diagram represents, it is important to help us determine the age of a star. So for example, the sun is about 1.4 times more luminous today than when it first reached the zero-age main sequence, and it will continue to increase over the next 5 or 6 billion years of its main sequence life. This can create great changes in our environment and other planets. Just a few % increase in the sun's luminosity can cause a temperature change of 2 degrees Celsius on our own planet, which would result in the melting of the polar ice caps unless compensation occurs. What ends up happening is once we end our main sequence stage, our star starts to expand, and this is where we start to go from main sequence to giant. And this can be determined based on the lifespan of said star. We can also follow a star's change from main sequence to the stages beyond, such as going to the red giant stage. In the HR diagram, the low mass stars like our sun will move up and to the right of main sequence region. So it goes up, right, up along the red giant branch. The star will grow steadily larger and move up in luminosity over about 1 billion years while it's looking for new equilibrium, causing its core to shrink and heat, because there's something cool about a star that's constantly happening. There is a war inside the core of the star where gravity is trying to pull it in, just as the production of energy is pushing back out. So when you no longer have nuclear fusion occurring, gravity starts to pull in the star, which causes an increase in heat, which allows for the star to be able to start going beyond just using hydrogen as energy. And so we go back into thermonuclear fusion, going in helium. And it will go into higher and higher and higher elements until it's finally created iron in its core. High mass stars, though, will rapidly drop in surface temperature as a relatively steady luminosity, causing their track to go nearly horizontal to their path, rather than going up or down. So they pretty much stay the same luminosity because they're already kind of big. And it's just because they're already really hot, so they're already super luminous. And they're expanding but cooling off some, causing them to basically remain the same. Just maybe they'll be red giants instead of blue giants. For now, we're going to leave this alone. We're going to come back to it in the future. And we're going to go back to apparent and absolute magnitude, where we will be looking at how to use and find these for stars, which we will use for our next lab. So you will need both of these to use the HR diagram. Finding apparent magnitude. Hipparchus' system of finding magnitude was used until the late 1700s, when it became possible to have more accurately measured stellar magnitudes. William Herschel modified this system into what we use today, and he determined the difference in brightness between the average of 20 first magnitude stars, or m equals 1, and the dimmest visible star to be a factor of 100. So the average first magnitude star is 100 times brighter than a sixth magnitude star. And since this is a difference of 5 magnitudes, the difference in brightness between each magnitude is equal to 5 square root of 100, which gives us about 2.512. But we're going to round that to 2.5 for simpler calculations, producing the table we see below. There are stars dimmer than +6, and we now have telescopes that can see much, much, much dimmer stars to this. So basically, our difference in brightness is going to be based on this. So if you have a magnitude of 5, you are going to do 2.5 to the 5th power, and that will give you essentially 100. And we're going to go over this a little bit more. It's going to start to make more sense, and then when you do it in the lab, it'll make even more sense. So now we're going to do an example. If one star, and we're going to call it star A, is a first magnitude star, so m equals 1, and our second star, or star B, is a third magnitude star, what is the difference in brightness? You want to find the difference in magnitude between the two stars. And so what we're going to say is, oh, it's 3 and 1, correct? So we have 3 minus 1. Difference in magnitude. 3 minus 1 equals 2. Second stage. We now look for the number 2 in our left-hand column. Aha! I have found it! Difference in brightness is 2, because you subtract the magnitude. You always subtract the highest number from the lowest number. Step 3. We find that, right? Now we read horizontally across to the difference in brightness column, which is over here. And we can see that our difference in brightness is 6.25. Right? So now let's have you do it yourselves. I'm going to give you a few seconds. I want you to try to find out each stage on your own before we move on. So in this one, star A has an apparent magnitude of 4. Star B is -1. What is the difference in brightness between the two stars? Which is brighter? So first, find the difference between the two stars. 4 minus -1, so it becomes plus, and that's how you get 5. Now I want you to find 5 in the table, and you're going to go directly across, which should give you a difference in brightness. So your difference is 100 times in this instance. So then, which star is brighter? Star B. Why? The closer it is to 1, the brighter the star is. This means brighter. And going this way means dimmer. So in this case, the higher the number, the dimmer the star. So how do we determine a star's magnitude? Star A has an apparent magnitude of +5. It is 4,000 times brighter than star B. What is the magnitude of star B? Let's find out. Difference in brightness, 4,000, breaks down into 40 times 100. So now you're going to go back to that chart, and you're going to look at it, and you're going to say, okay, well, to what power is 2.5 to what power gives us a 100 times difference? In this case, for 100, it is 5. And in the case of 40, it is 4. We're going to take those two numbers. We are going to add them together. So now we're going to do 2.5 to the 9th power. So the difference in magnitude is 9 magnitudes. Now what do? We add 9 to 5. Okay, because m has a plus 5, we know there is a difference of 9. 9 plus 5 gives us 14. Therefore, star B has an m of plus 14. How do we know we add it? Because we say star A is brighter than star B. Therefore, whatever we find gets added to star B and making it the dimmer star. If it says star A has a magnitude of plus 5 and star B is 4,000 times brighter than star A, what is the magnitude of star B? In this case, then you would subtract 5 minus 9. So if it was the opposite way, where star B was brighter, then you would do 5 minus 9, which would equal -5. So we would have an m of -5. Does that make sense? But because they say star A is brighter, that means you add it together and get plus 14. So finding absolute magnitude is a bit different than apparent magnitude. It uses more math. And to calculate absolute magnitude, a distance has to be chosen at which the stars are able to be compared with each other. Astronomers have chosen the distance to be 10 parsecs. I'm going to write that number here. Whereas 1 parsec is the distance at which a star would have a parallax of 1 arcsecond, which is equal to 3.26 light years. This is the actual comparative distance. 10 parsecs is where a star would have a parallax of 1 arcsec, and therefore 32.6 light years away. To calculate absolute magnitude, the apparent magnitude and distance must be known. So m is calculated with a known distance, which is 10 parsecs, always. Let's look at an example. A star has an apparent magnitude of plus 6. It is 100 parsecs away. What is the absolute magnitude? Step 1. We are going to calculate the change in distance, which is needed to bring the star to the distance of 10 parsecs in order to, and so we have to use whichever equation down below, which will give us a number greater than 1. Okay, so we are physically pretending to pull our star closer to us to make it at 10 parsecs, all right? So if you want to bring the star closer, you're going to use this first equation here, which if you're taking notes or you're using the PDF to take notes on, I would circle this and write bringing the star closer on top, versus if you're moving farther away, in order to get to 10 parsecs, you're going to use this equation. And this is very important. This is going to be very important in your lab, and you need to remember this, especially when it comes to working on the exam, in case this is on the exam. And so here we're going to calculate it because we're using this one, because we're changing and coming closer. So the change of distance is equal to, remember, we are at 100 parsecs and we need to get to 10. 100 parsecs over 10, which gives us the change is 10 times closer. So now we're going to move on to number 2. So we're moving 10 times closer, as we figured, okay? And the change in brightness because of change of distance, okay? Remember the inverse square law, where it gets doubled. So change in brightness is 10 times closer, so we do 10 to the second times brighter because of how much closer we will be, because 10 squared gives us 100 times closer. We have to increase in brightness would be 100 times if the star was brought to 10 parsecs, all right? So based on the previous step where we did 100 over 10, which gave us 10 times closer is how much we're moving, we need to then square that. Okay, that's step 2 is you square it. And so now we know we become 100 times brighter. And that's how we get to step 3, which is if the brightness is an increase of 100 times, what is the absolute magnitude? So now we're finding absolute magnitude here, in which case we're going to go back to that initial chart we used for apparent magnitude. We're going to say, okay, 2.5 to the what power is going to give us 100. And based on that chart, we know that 5, it is 2.5 to the 5th power that will give us 100, which means we will have a brightness change of 5 magnitudes. And since we came closer, the star would become brighter. And given the star has an apparent magnitude of plus 6, we are going to subtract. So 6 minus 5 gives us 1. which means our absolute magnitude is +1 because we did not receive a negative. So we take all this information and we create it into an HR diagram. We need to know the following: the luminosity, absolute magnitude, spectral class, and temperature. Also, for your lab, you will be comparing solar luminosity to absolute magnitude on a log scale. Let's have an example. We're going to start with a star that has a spectral class of 04 and a magnitude of -8. So you're going to draw a line like this, and you're going to put a dot. And then we have 05, M of 3, etc., etc. And so what we can see is that you have a trend forming here. And of course, you're going to have some outliers as your whole thing goes on. And so you can see, oh, hey, look, a trend. We can outline it. Well, guess what? That is your main sequence set. That right there is your main sequence stars. And what you have out here is going to be, for example, your I'm trying but I'm still failing group, or your dwarfs, your scientific issue kid. And so basically you can take this data that you have and look at it and say, oh, look, I can say, hey, this trend right here is our main sequence. I can tell that because they follow a pattern that we expect, whereas these outliers would be our dwarfs because even though they have a high spectral class, their absolute magnitudes are pretty low, which means they're probably quite small. Same thing if you found some out here, which would be our giant stage because, well, look, they have a high luminosity, but a very low spectral class, meaning their temperature is low, but they're still being very luminous, which must mean they're very, very big. And that's it for our class today, guys. I hope you enjoyed it, and I will see you all next time.